and welcome to lecture 38. We started discussing about design of low speed axial flow compressor. So in last lecture we started discussing about transformation or use of low speed facility in order to test high speed compressors, and we have discussed some of the important aspects that's what need to be considered. So today, as we have discussed in last lecture, we will be starting with the data that's what is given to us. Now here in this case, we will be starting with our initial case. We will be discussing today how to start doing the design using the free vortex concept. So let's move it. So we are asked to do design for free vortex concept or using free vortex concept. Second, that's what is by using our fundamental method, and third, that's what is by using force vortex method. Now for all this method, as we have discussed during our classes, very first thing that's what we need to do is we need to do our calculation at the mid station. So here this is what is a hint. It says we need to do our calculation at the mid station. Suppose for present case we are doing our calculation at 50% span because this compressor is a low speed compressor. So at mid station we need to decide with what is our mean diameter. We need to do our calculation for different velocity components and different velocity flow angles. We need to use our fundamentals of velocity triangle. We are looking for peripheral speed, we are looking for axial speed, mass flow rate, all these parameters, that's what is coming into the picture. Based on that, we need to calculate different entry and exit flow angles, absolute flow angles. We need to check with what is our degree of reaction, diffusion factor, de Holler's factor. We need to calculate different angles called camber angle, deviation angle, stagger angle, and based on that we will be making our framework, initial framework. Then what design method we are adopting or what design approach we will be adopting, that's what will be modifying my calculation at different stations. So fundamental part for all the three design discussion, that's what will remain same. Our initial calculation, that's what is happening at the mid station or mean section. Now what all data that's what is available with us is my entry temperature, entry pressure, what pressure rise we are expecting, our efficiency that's what is given 80%, mass flow rate is 4 kg per second, rotational speed is 2400 rpm, tip diameter is 400 mm, aspect ratio given is 1 and chord is given 100 mm. And one more parameter, that's what is flow coefficient based on tip peripheral speed is 0.73. Let's assume some data, we will be having gamma equal to 1.4. My work done factor, that's what we are assuming to be 0.98. My entry flow angle and exit flow angle, it says 0 degree. And specific heat at constant pressure, that's what we are taking 1.005 kilojoule per kg Kelvin. Okay, now let's start with. So our fundamental, that's what will be remain here. It says suppose this is what is my rotor. At the mid section I will be calculating my CW, that's what is my whirl component at the exit. If my mean diameter or the radius is known to me, I can calculate my CW into R equal to constant. That's what will remains constant throughout my span. Here in this case it is given my entry flow angle, that's what is 0. I have axial entry, that means my whirl component at the entry CW1, that's what is equal to 0. Now once we calculate this constant, we need to apply this constant in CW into R, that's what is equal to that number, and that's what we will be applying at different radius. That's what will be giving us what will be my whirl distribution at different stations. Now once we are calculating our whirl component, we are able to calculate our blade angles, we are able to calculate our flow angles, we are able to calculate all parameters which we are looking for at different station. So at this moment, let's see, suppose say this rotor I'll be dividing into 11 stations. Okay, and this is what is my mid station, that's what is at say 50% of my span. Okay. Now let's start with, so very first thing, that's what is, we need to calculate what is our mean diameter. So what all we know, we are given with the aspect ratio. So here if you look at, this is what is, say I can say this is what is my rotor and this is what is my stator. That's what is having aspect ratio is 1. That means my height of the blade to chord ratio, that's what is say 1. Okay. So I can say my height, that's what is equal to 0.1 meter. Now we have given our tip diameter, that's what is say 400 mm. So if my tip diameter, that's what is known to me, and if I know what is the height of my blade, we can calculate what will be my hub diameter and what will be my mean diameter. So here in this case, if we consider say my hub diameter, that's what we can write down. This is what is equal to 2 times dh by 2 minus height of my blade. If we are calculating that, it says my hub diameter, that's what is coming 0.2 meter. We can calculate what will be my mean diameter, it is nothing but my average d tip plus d hub divided by 2, that's what is giving me my mean diameter to be 0.3. So this is what is the location where we will be doing all our calculation for the initial stage. Now once we know what is our mean diameter, we can calculate the peripheral speed at the mid station. So my peripheral speed at mid span, we can say it is pi into dn by 60. Since my rotational speed is given, that is 2400 rpm, my mean diameter we have calculated 0.3, that's what is giving say peripheral speed at the mid span as 37.69 meter per second. Okay. Similarly, we can do our calculation at the tip station because my casing diameter is also known to me. So we can write down it is pi into n into dt by 60. My tip diameter given, it is 0.4. Okay. So that's what is giving my tip peripheral speed as 50.26 meter per second. Now very important parameter for us is to calculate the axial velocity. Since we are given with Ca by u tip, that's what is 0.73. So based on that we can calculate what will be our axial velocity. So it says my axial velocity, it is coming 36.69 meter per second. Now this axial velocity, that's what we are assuming constant throughout my stage. Okay. So this is what will be helpful for us to go with say next step calculation. So now we know what is our axial velocity, we know what is our peripheral velocity or peripheral speed. So next thing, that's what is to calculate what will be my flow angles. Okay. So if we are looking for the flow angle, say it says I am having axial entry, so my alpha 1 at mid station, that's what is equal to 0, and based on this velocity triangle we can calculate what will be my beta 1. Okay, that is what is say my relative flow angle. So that's what we can write down my tan beta 1 equal to um by Ca. Since my peripheral speed at mid station is known and axial velocity is known, that's what will be giving me my beta 1, it is coming 45.77 degree. Okay. Now no other parameter, that's what is known to us at this moment for the further calculation. So what we will be doing, say we will be taking, it says I am expecting pressure rise of 1000 Pascal through this stage. Okay. Under that configuration, what we will be doing, say at the mid station we will be taking this say 1000 Pascal pressure. So it says at exit my total pressure I can calculate, it is P01 plus delta P0, that's nothing but 101325 plus 1000, that's what will be giving me 102.32 kilopascal. So now I have my total pressure at the outlet, I have my total pressure at the inlet. Once we know this pressure at inlet and outlet, we can calculate what will be my pressure ratio. So it says if we are taking P02 by P01, it is coming 1.0099. Okay. Now since we know what is our pressure ratio, we can calculate what will be my temperature rise, total temperature rise. So we know from our fundamental, we can say my P02 by P01, that's what we are writing as a P01 plus delta P0 by P01 to the power gamma minus 1 over gamma minus 1 into T01 divided by polytropic efficiency. Now for this case, my entry temperature, it is given, it is 298. Our efficiency also is given, it is 80%. So we can calculate what will be my total pressure rise in a stage at mid station. That's what is coming 1.0467 Kelvin. Now this is what will be very helpful to us for moving further. Now be careful when we are not having any data, just dig in the details what is available. If not, then maybe you need to go with certain assumptions. So that is also one of the possibility. Okay, if you recall when we were discussing how to decide with say per stage pressure rise for initial stage, for say middle stage and for rear stages, there along with pressure ratio and efficiency, we were given with delta T0 range also. So that is also one of the startup for our calculation. Okay, so keep that also in mind. Okay, now here what we know, we can compare our aerodynamic work and thermodynamic work at mid station. So we can write down Cp delta T0, that's what is say my work done factor UCA 10 beta 1 minus 10 beta 2. Here in this case my delta T0 is known to me, my work done factor is known, peripheral speed at mid station is known, axial velocity is known, and beta 1 we have calculated. So that's what will be giving me what will be my relative blade angle or relative flow angle at the outlet of my rotor. So this is what is coming, say 14.1 degree. Now we can say we have data, that's what is available. We know what is our beta 1, what is our beta 2. So once we know what is beta 1 and beta 2, we can calculate what will be my blade deflection angle, or we can say what will be my delta beta. So it says my delta beta at mid section, that's what is coming 31.66 degree. Okay. Now we want to calculate what will be say total amount of work, that's what is required, or what need to be the power supply to this kind of compressor. So in order to do that calculation, we can calculate what is our specific energy. You can say that's what is Cp into delta T0. Since these numbers are known to us, we can say that's what is coming 1051.93 joule per kg. Now we are looking for what will be our power consumption. We can write down that's nothing but mass flow rate into specific energy. If we are putting that number, it says my total work required or power input required to run this compressor, it is coming 4.20 kilowatt. This is what is very important when we are deciding, say, making these experimental facilities. So this is what will be giving like roughly what need to be my specification for the motor. Okay. Now once we have calculated what all we know about beta 1, beta 2, alpha 1, we will be doing our further calculation for other angles and velocity components, because that's what is important for calculation of our parameters called say diffusion factor, degree of reaction, for all other flow angle calculation. These are the fundamental requirements. So we can say if we are looking at this outlet velocity triangle for the rotor, we can say my 10 beta 2 at mid station, that's what is given by u minus Cw2 divided by Ca. Okay, now that's what will be giving me what will be my say tangential speed or what will be my swirl velocity. So my swirl velocity, that's what is coming as say 28.47 meter per second. This is what is very important for us, because we are discussing at this moment design using free vortex concept, where we are looking for our tangential velocity component or whirl velocity component into radius, that's what will be coming to be constant. So this is what we are looking for. Okay, now based on this velocity triangle, we can calculate what will be our alpha 2. This 10 alpha 2 we can write down, that is Cw2 by Ca, and that's what is coming 37.8 degree. Do not get confused in sense of Ca1, Ca2. We have assumed our axial velocity to be constant. Okay. Now all these numbers, they are known to us. At mid station we can calculate our degree of reaction, because my degree of reaction, that's what is given by Ca by 2u 10 beta 1 plus 10 beta 2. This blade deflection angle or my blade angles or relative flow angles beta 1 and beta 2 at mid station, they are known to us. We can put in this equation, and that's what is giving me my degree of reaction at mid station to be 0.62. Okay, we can say this is what is a reasonable number at this moment. Okay, now we are also looking for the number, that's what is called d'Huller's factor or d'Huller's number, that is nothing but my relative velocity ratio. So let's calculate this relative velocity component. So if we are talking about the entry, we can say my V1, it is given by Ca by cos beta 1. Okay, since at mid station we know what is our cos beta 1, that's what is giving me my relative velocity at the entry as 52.6 meter per second. Okay, same way we can do our calculation for relative velocity at the exit, that's what is given by Ca by cos beta 2. If we are putting that number, it says my relative velocity at the outlet, it is coming 37.83. Now physically we need to understand these numbers. You are clear with what we say when my relative velocity is coming to be lower at the exit, that's what is representing my diffusion work. So that's what we are doing here. Okay, and it says like if I'll be taking the ratio of these relative velocities, that's what is coming 0.72. So this is what is in a reasonable range at this moment for the mid station. So we can say degree of reaction, it is 0.62. This is what is 0.72. Now our third parameter, as we know, that's what is to check is diffusion factor. Now in order to do the calculation for the diffusion factor, we are looking for the solidity to be known. So let's move there. We can write down say our pitch, that's what is given by pi d by z. Z is nothing but my number of blades. So at this moment, let's assume number of blades to be say 15. Okay, now if we are putting this number of blades to be 15, it says my pitch is coming 0.0628 meter. We will discuss how exactly we are coming with these numbers, but let's assume at this moment say 15. Okay, we will be discussing, this is what is very important parameter, because we know this is what has direct impact on what all we say in sense of aerodynamic diffusion. Okay, now we know my solidity, that's what we are representing in sense of say chord to pitch ratio, and chord, it is known to us, it is 0.1 meter. So we can write down my solidity, it is coming 1.59 at the mid station. Okay, now once this solidity we have calculated, our important aerodynamic parameter Leibniz factor, or we can say diffusion factor, that's what at mid station can be calculated by 1 minus cos beta 1 by cos beta 2 plus cos beta 1 divided by twice gamma twice sigma, and this is what is tan beta 1 minus tan beta 2. So if we are putting all these numbers, because my cos beta 1 it is known to us 45.77, say my cos beta 2 is 14.11, and solidity we have calculated as a 1.592. So based on that, it says my diffusion factor for rotor at mid station, that's what is coming 0.45. So this is also at this moment a reasonable number. Now let me tell you, say what we were discussing in sense of selection of number of blades. Suppose say this number at mid station, that's what is coming say lower. You can understand you need to play with the solidity. So maybe you need to change the number of blades, because my chord, that's what is given, it is fixed based on my aspect ratio. So you can change the number of blades and you can play with in order to set your diffusion factor in the range. Okay. Now, after doing all this calculation, we are more interested in calculating our different flow angles. Suppose if we are looking here, we are looking for what will be my camber angle, what will be my stagger angle, what will be my incidence angle, and what will be my deviation angle. Okay. So if we are considering, say we can use our Carter's rule for the calculation of M factor, and as we have discussed for say particular aerofoil, suppose if we are considering C4 aerofoil, for that my A by C ratio we have already discussed. A by C, that's what is representing the location where I will be having maximum camber. So that's what it says, that need to be in the range of 0.4. Suppose if we are considering NACA or NACA profile, for that this will be coming 0.5. So we will be putting that in order to calculate our M parameter. Okay. If you recall, when we are using different kind of camber line, there also based on stagger angle calculation we can use this M parameter, or based on the M parameter we can calculate what will be our stagger angle. So do not forget those plots also. Okay. Now what we know, my say camber angle, that's what is given by delta beta at mid station minus incidence angle divided by 1 minus M into say my pitch to chord ratio in sense of square root. Now if we recall, we discussed when we are doing our axial flow compressor, from initially only we need to provide the incidence angle. Okay, and as we have discussed, we can safely take the incidence angle variation in the range of plus or minus say -2. So at this moment for mid station we are taking our incidence angle to be 0. Same way for the tip section we will be assuming say -2, and at the hub we can assume safely to be +2. So let me take this incidence angle that to be 0. Okay, this is what is our assumption. This delta beta, that's what is known to us, so we can calculate what will be our camber angle. It says this is what is coming 41.49 degree. Okay. Now once this number, that's what we have known, we can calculate what will be our deviation angle. So this deviation angle, that's what is correlating my M parameter, what will be my camber angle, and what will be my say solidity. So if we are putting this number, it says my deviation angle, that's what is coming as a 9.83 degree. Okay. So this is what we have discussed earlier also. This is what will give rough estimation for the deviation angle. Later on we will be using, or say you will be using, or people they are using say computational tool in order to understand what is happening on the suction surface, and mainly what is happening near the trailing edge, and based on the expectation this deviation angle they are going to change. Okay. Now this is what is say our deviation angle. Okay. Next, that's what is the calculation of blade setting angle or our stagger angle. So this stagger angle we have discussed, that's what is in a function of beta 1, incidence angle, and theta m by 2. If we are putting all this number, it is coming 25.02 degree. So we can say at mid station we are able to calculate what all parameters we are looking for. Now let's see what all we have calculated. So let me put it here. So here if you look at, say this is what is say my radius ratio, my mean radius, that's what we have taken as 0.15, okay, and my area, that's what is say 0.09 meter square, flow rate, that's what we have taken as a 4 kg per second, peripheral speed at mid station we have calculated, axial velocity is known, we have calculated our alpha 1, beta 1, we have calculated what will be my beta 2, what will be my delta beta, specific work done, CW1 we have taken that to be 0, CW2 that's what we have calculated based on aerodynamic and thermodynamic work. We can say we have calculated our degree of reaction, our relative velocities at the entry and exit. Based on that we have calculated relative velocity ratio. Then we have calculated our M parameter in order to calculate say diffusion factor, in order to calculate different flow angles. Now this is what is advisable to all designers. It's your choice. So we will be doing our initial calculation using pen and paper. Then after we will be using Excel sheet. So we will be calculating our all parameters at the mid station. So as we have discussed, we can use our Excel sheet. That's what is giving so much of flexibility. You will immediately realize what all will be the use. So you have done calculation using pen and paper, and those numbers we have calculated. That's what we have converted into formula form, or we have made our Excel sheet program. So these all are the parameters which we have calculated with. Okay. Now here in this case my delta P0, that's what we have taken to be say 1000 Pascal. Okay. Now as we have discussed, now our next target, that's what is to calculate the distribution of CW2 at different stations, at hub, at mid and at the tip. At mid station we have done our calculation. Okay. Now we know what is our hub diameter, we know what is our tip diameter. What we can do, we can divide that into equal number of stages. As we discussed, at this moment we are dividing that into say 11 stations. So let's do the calculation what is happening at the hub and what is happening at the tip station. Okay, how do we calculate? So here now my CW into R equal to constant, that's what is coming 4.27. So at any station, this radius, that's what is known to me, this constant is known to me, I can calculate what will be my CW. So let's see. So we will be putting this as a CW into R equal to constant. That's what we have done calculation. It says 4.27. Now based on this formula, at any station we can write down what is our work component. It is constant divided by my radius, and beta angle at particular station also that we can calculate. It is U minus CW2 divided by CA. So at hub, if we are considering, we know our hub radius, that's what is coming say 0.1. So if we are putting that number, it says my work component at the hub, it is say 42.7 meter per second. Our beta 2, that's what we are calculating at the hub, it is coming minus 25.59. Same way we can do our calculation at the tip station, because at tip we know our radius, that's what is 0.2 meter, that's what is giving 21.35 meter per second, and my beta at the tip, beta 2 at the tip, it is 38.23 degree. So you know the way in which we have done our all parameter calculation, that's what can be done here. So what we mean is we can do our calculation for alpha 2, we can do our calculation of relative velocities, we can do our calculation for degree of reaction, we can do our calculation for pitch, we can do our calculation for diffusion factor, then we can calculate all angles. So let me put it in a compilation form here. Okay, so here if you look at what we have done, say this is what is Excel sheet program dot what we can make, or you need to make a practice using the Excel sheet programming. That's what is little easy and flexible to us when we are doing the design part. So this is what is our mid station as we have discussed, and this is what is representing my hub station, where our radius is 0.10, and at the tip station my radius, that's what is 0.20. Okay, and this is what is all my calculation at the mid station. If you consider here this Excel sheet program, it is designed in such a way we can do our calculation for CW into R at mid station, that's what is coming 4.27. Now here in this case we need to calculate our CW2 at the hub station. That's what we have discussed, CW divided by R. Same way we need to calculate at the tip, because my constant is known, so we can calculate what will be my CW2. Once this CW is known to us, we can calculate what will be our alpha 2, what will be our beta 2, degree of reaction, velocity ratios, and as we have assumed our number of blades, that's what will not change, that will be 15. So that's what is aspect ratio is 1. My chord also we are assuming say constant from hub to tip, that's why it is 0.10. We can say we can calculate our diffusion factor at hub, we can calculate our diffusion factor at the tip. You can see the variation of these numbers. So here in this case, if you look at my degree of reaction, that's what is coming 0.15, and as we have discussed first cut check, that's what we need to check with my degree of reaction at the hub should not go 0 or negative. We can say this is what is reasonable number 0.15 at the hub, it's okay. Now here if you look at my delta beta, that's what is coming to be large. We have decided that should not increase 45 degree. But if you recall, when we were discussing different design approach, that time we have discussed my delta beta for free vortex concept at the hub, that's what will always be coming to be higher. And the reason is not because of any other thing, this reason is because my hub radius and my peripheral speed at the hub, that's what is coming to be lower, and that's the reason my delta beta is coming to be higher. And here if you look at, as we have discussed, my diffusion factor, that's what is coming to be 0.29 at the hub, 0.45 at the tip, and 0.39 at the tip, and at mid section it is 0.45. Okay. Now this is what is representing our relative velocity ratio, that's what we say D'Euler's factor, and that is also coming in a reasonable range. So we can say this is what will be giving us idea about how do we do our calculation at different station. So at this moment, if we look at what we have done, say we have started calculating our parameter at the mid station. We have calculated all our parameter at the mid station, that's what is required for making of our blade. Then once we have understood CW into R equal to constant, that's what is a law for free vortex. Based on that concept, we have done our calculation at the hub station, and based on the same concept, we have done our calculation at the tip station. Now that hub station, we have our CW2, that's what is different. At tip station, CW2, that's what is different, and that's what will be giving us idea for calculation of what all parameters we are having. So here we are stopping with the calculation at 3 different locations: hub station, mid station, and tip station. We are at this moment discussing the design of rotor. Now in next lecture we will be discussing what all we need to calculate at different stations. How do we do our design for the stator? Thank you very much.